So in this laboratory video, we're going to discuss the concept of taking pH of a solid sample. And this solid sample is going to be soil, aka dirt, but quite honestly, those two are not the same thing. Just for clarification purposes, soil is actually the dirt that you would associate with, but the definition of dirt is really remnants. All right, so imagine remnants of particles around in your house. That is basically dirt. That is not soil. Soil is what you would find out in your backyard, front yard, or whatever the case is. So in this laboratory experiment, what we're going to do is we're going to go around to a couple of different locations and we are going to gather some soil samples. All right, and then we're going to bring those soil samples back into the laboratory and we are going to measure the pH of that solid substance. Now, this is kind of weird and strange, and the reason is because pH, if you've measured pH so far in a laboratory, most of the time this has been in a liquid solution. And really, we're going to get to that point in this laboratory method. It's just a processing technique that we have to do. And quite honestly, the only reason that we are doing this laboratory in this particular class is because we are going back to the basics. We're going back to the roots of methods and following methods as they are written. All right, so over here to the side, what I'm going to do is I'm going to write the word method, and this is the method that is from the EPA. And the EPA, of course, is the Environmental Protection Agency. So if I was a laboratory company and I wanted to measure the pH of soil, well, this is kind of my starting document right here. So this method would then get turned into typically a standard operating procedure. And the SOP is something that my company would write based on what I have in our laboratory, following our rules in our laboratory. So methods are the origination source, and again, the SOP is going to be adapted and modified in order to fit my particular company. And quite honestly, it really is preferred for all companies to have their own SOPs, not to just basically print this method off and do it. However, just to get you experience with this method document, this is what we're going to follow, the exact method from the EPA, and that method is 9045D, 9045D. All right, so number one, it says the method is an electrometric procedure for measuring pH in soil and waste samples. So if you wanted to measure the pH of sludgy poop, then you can bring that in without a problem and measure the pH of it. It says waste may be solids, sludges, or non-aqueous liquids. And if water is present, it must be less than 20% of the total volume of the sample. So a couple of things here that I want to say. Number one, electrometric. Electrometric basically is referring to probe wear. Probe wear for pH runs off of electrometric procedures. It's really a conductivity that is going on, and it's transferring that conductivity to a pH meter, and that pH meter is the box that shows the number on the screen that you write down. So a probe is not the same thing as the meter. Okay, a lot of people think that it is, but that's a misnomer. The probe is what you are putting down into your sample that is doing the measurement. And that measurement is getting relayed to the meter that converts that voltage into a number that we associate as pH. So that's pretty important, and a lot of people get confused with that. Next, measuring pH. Well, for those of you that have not taken maybe a general chemistry course, pH is going to be the negative log of the hydrogen concentration. So that is the equation that we typically use for pH whenever we talk about it. That equation is very important to memorize, all right? That equation we will use all the time. And don't be surprised if you're working for a company and auditors come around and they ask you these types of questions. Oh, you've been working with pH for over the past year? Well, what is the pH equation? Just for them to test you and gauge you on your knowledge of what you're actually doing in the lab. Of course, 7 is going to be the neutral, and anything below 7 is going to be on the acid side, so 1 through 7, and then anything above 7, of course, is going to be on the basic side, and that's going to be 7 through 14. However, we also call this alkali, so either one of those would work, and those two terms are interchangeable. The reason that I'm giving you the equation is because you could be asked to solve for pH. Now, there's different types of questions that could come your way, and if you've taken a Chemistry 151 or 152 in particular, you've often heard of acid dissociation constants. Acid dissociation constants are represented as Ka, so acid dissociation constants. There's two different types of acids that you would find in a laboratory. You would see some that are very strong and some that are very weak. There really is no rhyme or reason on which one's which, and this is just something that you would have to memorize. There's only really 7 strong acids in total. The rest of everything else that we use in a laboratory environment are classified as weak. All right, well, if they're strong acids, the good news for you is that you can directly use the pH equation and plug in some concentrations and solve for the pH. Well, what 152 in particular would do when you take that class, if you do, is that will focus on a weak acid. And a weak acid is basically something that does not give up all of the protons, right, that it has with it. So, acid disassociation, if you disassociate yourself with someone, you're breaking the ties, you're breaking the connection. You might not be hanging out with them as much, right? The same thing happens here with acid. Acid dissociation constant means that that hydrogen is going to stay around a little bit longer, and it doesn't want to associate with anything else in the solution. So it just kind of sticks to its own. It stays in its own little home of the acid molecule, and it never gets out, and it never ventures, and it never goes off and mingles and socializes. It's like a little hermit hydrogen, right? So there's kind of a background of pH and the pH equation. How do I solve for a pH equation? Well, pretty simple. Most of the problems that I would give you at this point would be, let's say that the concentration of hydrogen in the sample is 0.0043 big M, and that big M stands for molarity. What is the pH of the solution, right? Okay, well, basically what you need to do is take the pH equation, negative log of the hydrogen content. Well, right here is your hydrogen content, and keep in mind it always has to be in terms of molarity. And I will give you molarity almost every single time. I mean, that's not really the purpose of this lab or what we're doing as of this moment, right? So the only thing that you have to do is take that number, plug it into the hydrogen equation, and then log it, and then negative that number. So whatever answer shows up on your calculator when you hit negative log of 0.0043 would be the answer to that question, right? That's as simple as these equations should be. And those questions would not get any more complicated than that. So, in a roundabout way, what I'm saying is that when we measure the pH of the soil sample that we will bring into our lab, we are measuring the hydrogen concentration that has been released in that soil sample. That's what this is all about, all right? Summary of the method, section 2, says the sample is going to be mixed with reagent water and the pH of the resulting aqueous solution is measured. So there you go, right? This is a roundabout way to kind of do everything that we've done with pH so far. Yes, we are starting with a solid sample, but we're mixing it with some water, and that water is allowing us to get an aqueous solution that we will end up with, that we will eventually put our pH probe in and measure the pH. Section 3 is going to concern interferences, right? All methods, all measurements have some type of interference, and this is no exception here. So interferences, samples with very low or very high pH may give incorrect readings on the meter. This is very typical for a pH probe and a pH meter. If you are really acidic or if you're really basic, there is a lag, and sometimes it will overwhelm the pH probe. Now, sometimes you can overcome this by allowing the probe sit in that solution for a little bit before you immediately take a reading. But this method is kind of singling this out. It says for samples with a true pH greater than 10, the measured pH may be very, very low. So you can't necessarily trust that sample. The error can be minimized by using a particular type of probe, something that you would have to order, something that is more specialty, and this is called a low sodium error electrode. And the reason for this is how the bottom of the probes work. So when you go in and take a pH probe and you put it down into a sample, there's this jelly layer that's going to be here at the very end. And that jelly layer works with a hydrogen and sodium transport. This actually will switch places, and this allows this probe to measure slight potential differences at the end. That's how all of these pH probes work, right? That jelly layer is very, very important at the end of the probe. Well, what they're telling you to do here is if you do expect that this solid sample has a pH greater than 10 and you still want to measure the pH of it, then you need to use a special type of probe that is made with that in mind. And that is a modified gel layer on the end of these probes. Now, very often they are more expensive, and this jelly-like layer is called the sol gel layer. That's just kind of the particular type of word that we give it. In addition to that, it says strong acid solutions with a true pH greater than 1 may also give incorrectly high pH measurements. So once again, this is something that we need to kind of think about. If we're following the method and we do get something greater than 10 or less than 1, and we expect that it is greater than 10 or less than 1, then maybe we need to do something a little bit different other than just sticking a probe down into it, because these are interferences that we have to keep in mind. 3.2, it says that temperature fluctuations will also cause measurement errors. So if you were in a room and maybe during the summer it's going to be extremely hot, and then you're doing the same type of measurements in a room that's not temperature controlled, so therefore in the winter it gets really, really cold, you could see some fluctuations in the data if you were tracking this over a period of a year or a handful of months. So temperature is very important, and temperature of the soil sample and your actual sample that you're measuring, including that water that you're adding in, is also very important. So you want to keep those things as constant as possible, because if you do not, that temperature can cause changes in the pH readings, and you want to be consistent and you want to be precise. 3.3, it says errors will occur when the electrodes become coated. All right, so what that means is that sometimes, depending on the sample, your probe that you are using to measure the pH with, that probe at the very end can become coated with filmy, slimy residue. And over time, that residue will build up, and over time, it will prevent the pH probe from doing what it's supposed to do. So you've got to be very careful as far as cleanliness goes. So it says if an electrode becomes coated with an oily material that will not rinse free, the electrode can be cleaned with an ultrasonic bath. Well, this is like a jewelry cleaner. It just sends slight vibrations through the sample, and it literally shakes the vibrations, or the vibrations literally shake the contamination off. Or be washed with a detergent several times with water and placed in a 1 to 10 hydrochloric acid so that the lower third of the electrode is submerged. All right, so hydrochloric acid does a very good job eating away grimy, oily, organic type of material. But this is not hydrochloric acid straight from the bottle. It is a 1 to 10 dilution. Basically, what that means is that you're going to take 1 milliliter of hydrochloric acid and you will take 9 milliliters of water, and that adds up to be a 10. So that is a 1 to 10 dilution. So a 1 mil into a 10 mil volumetric diluted up to the line with water, or 1 mil and 10 mils of water if you don't need to be exact in a graduated cylinder, or 10 and 100, or 100 and 1,000. The ratios are still going to be the same. All right. Then finally, if that doesn't really work out for you and you have a problem with your probe, then number 3 says you got to clean it for the manufacturer's instructions. And if that doesn't work out, you probably need to trash it after that point. Section number 4 concerns apparatus and materials. This is just a section, again, in any method or SOP that kind of tells you what you need. It's the ingredients to the cake box here, right? So make sure that you have these things in play, and if you do have these things, then you probably can do this method without a problem. Notice it says pH meter, and then 4.2 says glass electrode. And this glass electrode is another word for a pH probe. Remember, I told you they are really labeled differently. A probe and a meter is not the same thing, and they've listed them each separately here. Okay, 4.3 is the reference electrode. Most of the time, the glass electrode and the reference electrode are in combination, right? So that's just the way that pH meters are made anymore. Used to, 30 years ago, we would have a pH probe and a reference probe to compare everything to, but now they just really make them together into one tool, and that tool is called the pH probe. So that reference electrode is already possibly and probably built in to that glass electrode that you're using. And we call that a combination electrode. 4.4 is a beaker, 4.5 is a thermometer, 4.6 is a balance, and then finally we get to section 5, which is classified as the reagents, right? We are kind of going through the typical format of a method here that you would see in a laboratory. Reagents, it says reagent grade chemicals shall be used in all tests, so you just don't want to go to the grocery store or the hardware store and buy things and bring it into the lab. You really want to order these things. You want to make sure that they come with certificates. You want to make sure they are what they state that they are and in the concentrations that they say that they are. It says, unless otherwise indicated, it's intended that all reagents shall conform to the specifications of the Committee on Analytical Reagents of the American Chemical Society. So ACS really is the label that we are looking for here, and ACS stands for the American Chemical Society. 5.2 is reagent water. It says whenever we refer to reagent water, we're going to go back and we're going to kind of define reagent water. What exactly is that? That's typically distilled or deionized water. And it's also water that you really want to be neutral, because if you are measuring the pH of a sample and you add water to that sample and that water has slight acidity or slight alkalinity, then you are going to be changing the pH of the soil or the sludge sample. So you do really want to make sure that that stuff is neutral, and if not, you want to make it neutral before you use it. 5.3 says primary standard buffer salts are available from the National Institute of Standards and Technology, or NIST, and it should be used in situations where accuracy is necessary. So primary standard buffers are really what's used to make sure that our probe is going to be calibrated. And these buffers typically that will be used are 4, 7, and 10. So pH of 4, pH of 7, and pH of 10. This is a way that we can quote, tear out our probe and make sure that it's calibrated and make sure that it is reading the proper pH level when we decide to use it. So literally what happens is that you take your probe and you will pick one of them. It doesn't really matter which one first, and you put it down into the 4 buffer and you tell the probe this is pH of 4. And then you put the same probe into pH of 7 and then the same probe into pH of 10, and really the meter takes over from there. So what begins to happen is that you will get a graph, a linear relationship, and that graph will be a straight line. And that straight line, the closer it is to the straight line, the better that your slope percentage will be, because we're looking at slope, which is how high or steep this line is going to get. That number is very specific, and that number is what it compares it to tell you if your probe is good or not. So this is a way that we can make sure that our meter is going to report the right number, and it's also a way that we can make sure that our probe is reading the proper way. So those buffers are fairly cheap. We order those buffers pre-made all the time. They do not have a long shelf life as far as you using them. So really you want fresh buffers if you're working in a real laboratory, preferably every day if you have to use them on a regular interval. Section 5.4 says secondary standard buffers may be prepared. If you want to use those, then those are okay. You just want to make sure that those are good as well. Section 6 is sample preservation, and it says really this is not applicable to you, because when you go out and you get these samples, you want to make sure that you measure the pH as soon as possible. So they do not want us to put soil samples into the refrigerator or leave them out into the lab for days before we get to them. They really would prefer us to measure them as soon as possible. Now, Section 7 is going to be the procedure of the method, and in Section 7.1, they're going to talk about calibration, and this is going to be calibration of the pH probe. This is something that's typically done in a wet chemistry laboratory every day or a couple of times throughout the day, and this is using the buffers like we have talked about from up above. It says because of the wide variety of pH meters and accessories, operating procedures are not going to be included here, because that's really based on your manufacturer. And this is really where your company's SOP comes into play. They know what pH probe they have, they know how to calibrate that particular pH probe, and they will go in and modify this method and include the directions on how to calibrate their pH probe in this system, right? That's the whole purpose of an SOP. That's the whole purpose of the modification. It says each analyst must be acquainted with the operation and familiar with the instrument. So we just don't want you to work blindly with a pH probe and you've never used it before. You've got to have some training on it, and there's proof of that training with your company. 7.1.2 says each instrument should be calibrated a minimum of 2 points, so at least 2 buffers. And they have to bracket the expected pH. Okay, so what that means is that if I do a 4 and a 10 only, right, and then I have a sample and that sample reads a 2, well, that sample is not going to be good. And that's because my pH probe was calibrated between the ranges of 4 and 10, and 2 does not fit in that window. So ideally, I should not report that number. If I do want to report that number, I'm going to have to expand my calibration window. I'm going to have to go lower than pH of 4, or I'm going to have to go higher than pH of 10. Well, the thing here is that I shouldn't probably go over 10, because we already know of a sodium error that could happen with my probe. So I could go lower if I want to. Maybe I could go down to pH buffer of 2 or a pH buffer of 1, but I don't really want to go lower than 1 either. And the reason we've already talked about, we get errors associated with the probes when we do. So it just gives you a little bit of more detail about what to do when you do calibrate them, when you do use your buffers. Just make sure that you are calibrating it and you are using a little bit of common sense as far as ranges go. Make sure that your samples fit within the range of the buffers that you are using. Notice also it talks about the temperature in this section, and it says the temperature of these samples should be within 25 plus or minus 1. So that also means that the temperature of your buffers will need to be around 25 plus or minus 1 when you decide to use them. Room temperature is typically always around 23 to 24 for us. So with that said, you're not going to see us put buffers onto a hot plate to heat it up with 1 degree. But if we were doing this for real and we were following the real SOP in a real employer's setting, then we would want to make sure that these buffers are at 25 plus or minus 1 when I begin to calibrate and when I begin to use them. Section 7.2 is going to talk about sample preparation, and this is of your soil sample, and that is what we're going to be collecting. So section 7.2 says I'm going to take 20 grams of soil and I'm going to put it into a 50 ml beaker, and I'm going to add 20 mils of reagent water. So I'm going to cover it so that way I don't lose anything, and I'm going to stir it continuously for 5 minutes. So this is where our automatic stir plates come in very handy. You do not have to stir this by hand. You put a magnet in it, you let it churn, you let it stir, and then 5 minutes later, you come back to that sample. So notice this is a 50-50 mix, right? 50-50 mix, 50% soil, 50% water at this problem. Or at this point. 20 grams of soil, 20 mils of water, 50-50. So put a magnet in it, put it on a plate, let's stir it. 5 minutes in total. It says additional dilutions are allowed if you are working with hygroscopic soils or salts or other problematic matrices. So sometimes when you add water in, that 20 mils of water, you might not actually get anything sludgy. What will happen is that that soil will suck up the water and it will still be a solid sample. So they know that those samples are out there and they know that they will exist. So the method is giving you a little bit of leeway to add some more water in until you can really get a liquidy solution to put your pH probe in later on. Section 7.2 says let the soil suspension stand for 1 hour before you do anything to it, and you will see some settlement that will go to the bottom of the beakers, and that's okay. So that's expected. You're going to see it, but you will not measure the pH until you let it sit for at least 1 hour on the lab counter or the lab bench. All right. 7.2 continues on. And it says take your probe, basically, and put it into the supernatant liquid. All right. So what that means is that if you have a beaker, you're going to get this sludgy stuff at the very bottom. There's where my soil's going to go. And then you'll see a little bit of clearish liquid that sits up here on top. That clear liquid is what you want to measure the pH of. All right. So when I put my pH probe down in here, I want to make sure that my probe is far enough down into this clear solution, but I do not want to cram it down in here or let it rest onto the very bottom of the beaker where all the sludge or some of the heavier types of clays might be that begin to settle out. So that is what we call the supernatant. It is the liquid that's above that sludgy, more solidly like material that settles to the bottom of the beaker. If I continue to go on, it says just make sure that your temperature is checked and in place, and if so, that requires a thermometer, so I should be recording the temperature of my samples as well. And then it says report the results as soil pH measured in water at blank EC, where EC is the temperature at which the test was conducted. So this gives me a little bit of insight about how I should be recording data into my laboratory notebook or data that the lab company might be interested in, and temperature is one of those. All right. Section 7.3 talks about sample preparation in waste material. And of course, we kind of know what waste material is now. So for instance, let's say that this is a solid sludge at the water treatment facility. Well, this sludgy type of material I would want to bring in, I would want to pH it, and section 7.3 is the section that I would follow for that purpose, okay? We're not going to be measuring waste materials, and because of that, a company might leave this section out if they will never measure waste materials, all right? If they know that they're only going to be measuring soil, then they will only put section 7.2 into their method, and they will not even put section 0.3 into the method. But this method does take care of that type of sample. That's sample. That's also money that your company could make. So why turn it away? And what you would see most of the time is that if you never tested waste material, that could still be in the SOP just in case a company would like to submit a waste sample for you to test. You are approved, you have an SOP for it, and your company can make money, giving you a paycheck in the very end. All right, so section 7.3 we are not going to talk about. I will let you go through this section on your own. You can skim it, you can read those directions just as well as I can to you, but because we are not working with a waste material, section 7.3 I'm actually going to cross out and just ignore, but please read it on your own spare time. Section 8 is quality control, and that's kind of an embedment into a laboratory to make sure that people are following the rules and following the steps and reporting data like they should. And it says report or refer to Chapter 1 for the QC protocols. Electrodes have to be thoroughly rinsed between the samples. And the reason for this is because, you've guessed it, cross-contamination. I do not want to bring a soil sample in and then not rinse it fully and clean it really well before I go on to the next sample, right? This prevents cross-contamination for me. Section 9 is method performance. Method performance is typically very heavy-handed calculations, very kind of common types of materials that come into the lab. Method performance takes a look at that data. It takes a look at those numbers to make sure that nothing is going out of line that it should not. This is pretty simple. I mean, it's not really a calculation here. It's just really a measurement, and that measurement is coming from a pH meter. So really your job has been completed if you are handling the pH meter the proper way. So you're kind of seeing empty sections for method performance. If a company that does this type of test with the same types of samples over and over, they could build up a database of data, and that they will allow to track and to look at for common out of specification types of samples that might come their way. But that really is kind of in the hands of the employer, not the EPA when this method was written. Section 10, which is the final section, is references. And this is just a couple of references that this method has been built upon or that it's taken information from. So there's kind of your overview of method 9045D. Here at the very end is a flow chart. What you're seeing is that the start of the process is going to happen up here at the very top, and it says 7.1 says calibrate your probe first. You want to make sure that's in working condition, and then it says is the sample soil or is it waste? And for us it's soil, so we go to 7.2 and it tells us to add 20 mils of water to 20 grams of soil, stir it for 5 minutes, let the soil sit for 1 hour or filter it, and then after that we go and insert our electrode into the sample, and then it says do sample and buffer solutions vary by 2 degrees? Hopefully no, if we've kept track of our temperatures. And then it says report your results and your temperature, and then that sample can be stopped. You can move on to the next one after that. You got access to this document in your lab folder, so you're more than welcome to kind of flow through the other parts of the flow chart, but these flow charts are very common in methods, especially when you have multiple different steps that come along with this whole process. And that's on the very last page of the method. All right. Okay, so what's going to happen here is that typically what we'll do is that we'll take you to at least 3 different locations, okay? And at each one of these locations, we are going to get a soil sample, and we are going to bring that soil sample back into our laboratory. From this soil sample, what we'll get you to do is we'll have possibly everyone in the class to measure a soil sample from that master collection, okay? And we'll get you to do it twice. We could call it A and B, or we could call it 1 and 2, but we'll get you at least to do duplicates of each one. That way you can do your first one, you can do your second one, you can compare those two, and hopefully those two will be really close numbers, right? So multiple replications of a measurement, always good for a laboratory. We never do really anything just one time and that's it. Well, this is from sample location 1. We'll also have a second location and a third location. So you could have a 1A and a 1B, a 2A and a 2B, a 3A and a 3B, and this brings your total amount of samples to 6 that you will be responsible for. All right, the prep work here, again, it's not very hard. Take some dirt, take some water, mix it together, let it sit for an hour, and then you put your probe in it and you measure the pH from the meter. Record that, record the temperature, and you're good to go. That's it. That's all there is to this lab. However, what will become more involved here will be the statistics from the lab data. Okay, and we're going to go back to the very first of the semester, and we're going to talk about the statistics equations again, because you've not seen those in a while, right? So the first one, of course, is going to be the average. So I'm going to have you to calculate the average of everything from the first location, everything from the second location, and everything from the third location. So you'll have 3 averages here that you will calculate using Excel. The next one is the standard deviation, and the standard deviation is S. So each one of these will also have their own standard deviations. So your 2 samples, as well as the 2 samples from everyone else in the class. That means if there's 10 people, each one of you did it twice, there's going to be 20 measurements that you will have to average for that batch, and 20 measurements that you will do a standard deviation of from that batch. All right, but we're not going to stop here. Excel can do that work for you too. It's just a simple code. Equal average equal STDEV. That is how you need to put it into Excel. The next thing is we're going to use a code that says equal count. All right. And when I type in equal count, what's going to happen is I'm going to highlight the data. Just like I did with average, just like I did with standard deviation, I just click and drag down and I highlight all the data that I want it to count for me. So count basically counts the number of data points that you have in your listing. So if there's 20, 30, 40 data points into that data set, you do not have to sit there and count them yourself. You can allow Excel to do that for you. The next one is going to be equal TINV. And TINV is basically the student T value. So when you key in equal TINV and open the parentheses up, it knows that you are wanting a student T value from that table. And I don't carry around a copy of that table. Excel has that table built into it. So the very first number that you need to key in here will be 0.05. And the reason is because unless otherwise stated, this is a 95% confidence window. Now, if it's not a 95% confidence window, I would want to take the difference. But notice that this is not in percentage, it's in the decimal form. So 95% is actually 0.95, right? So 1 minus 0.95 is 0.05. So this is the uncertainty that they are asking for in Excel. So for instance, if you want it to be 99% confidence, what you would key in into Excel will be 0.01. and that's because you are 1% uncertain of the number. Okay, if you are wanting 90% confidence interval, then what you would key into Excel here would be 0.5, not 0.05, right? Or sorry, no, 0.1, not 0.05. That is a 10% uncertainty, and that's what Excel wants. And then finally, the degrees of freedom. So the reason I wanted you to do the count is because with the TINV, this is degrees of freedom, and degrees of freedom will be the number of data points minus 1. All right, so that is your student T value. Finally, we're then going to do a 95% confidence interval equation, and that's typically taking your T value from the TINV and you multiply your standard deviation, and you do that together in one step. Divide it by the square root of n, and n is the number of data points, so that is your count function. That's another reason that we put that into an Excel. Okay, so there's the stats, and you'll have to do that on each set. So each set will have their own average, their own standard deviation, its own count, its own TINV number, but if it's the same number of people doing duplicates, same number across the board, it's probably all going to be the same for that one. And then your 95% confidence interval. Again, the 95% confidence interval is a plus or a minus number. So I would take my average and I would add the 95% confidence interval to it. And then I would take the average and I would subtract the 95% confidence interval to it. And then when I do that, that will give me my range. And I am 95% certain that the real pH is going to fall within that range. And that's the purpose of the stats. The other part that will go on here with stats before you do any of this is the Q-test. And the Q-test is, should I remove any point, right? That's the whole purpose of using the Q-test. So how do I determine this? I look for the really, really low number or the really, really high number in each one of these sets, okay? And I use the Q equation, which is gap divided by the range. And you can go back and review those if you need to. You know where those videos are in those tables. And if it does pass the Q-test, I cannot get rid of that point. However, if it does not pass the Q-test, then I can get rid of that point from the data set, and hopefully it will make my data look a little bit better. So I really want to focus on the high number and the low number here. Anything in the middle I can't really get rid of, right? It's only the extremities, the really, really low ones or the really, really high ones. So check, and you'll see that in the spreadsheet template, each data set for a Q-test first. You want to do this first. Because if you can remove a point, then that means that point should not be included in any of these over here to the right-hand side. That point should not be included in the average, the standard deviation, the count, the TINV number, or the actual 95% confidence interval calculation. Bottom line, leave it out, and you've got to do that first before you do anything else with the stats part of this lab. All right? So your work here is going to come from a little bit of calculation, a little bit more involved spreadsheet work, not actually lab work itself. Again, it's just a review of a method. It's a review of proper steps that we have to take, and this in particular will be coming from the Environmental Protection Agency because it is a soil, not dirt, lab experiment. So good luck with the lab. If you got any questions, especially with the spreadsheets and the calculations, let me know. You know how to reach me.